Hi, in the previous lectures, we have studied the relationship between stress and strain. In today's lectures, we will base on that relationship to study the deformation of members subjected to the most basic type of loading, namely axial loads. Let us start with the discussion of the so-called Saint-Venant's principle. For that, assume we have two identical, uniform, rectangular bars as shown on the screen, on which we draw a grid of vertical and horizontal straight lines of the same spacing. Now, if we subject these two bars to an axial loads of the same resultant but different distribution, we will observe the following. As you can see, while the distortion occurs to the lines near the fixed support and the point of application of the concentrated loads, that is not the case for the lines further away from those. So if the materials remain elastic, based on the stress-strain relationship that we learned in the last lectures, we can predict the distribution of the normal stress at the location of each vertical line. To visualize such distribution, let us section through each bar at two locations. And then plot the stress distribution on each cross-section of each bar. Since the vertical lines are distorted for the top bar, there is a clear difference in the stress distribution of the two bars in this region. Now, if we consider the cross-sections further away from the loads for the two bars, the stress distribution on the cross-section will be the same. All of these observations are referred to as Saint-Venant's principle. In short, this principle states that the stress and strain produced at a point in a body sufficiently removed from the region of external load application will be the same for the same resultant load, regardless of the load distribution. Now we will use the Hooke's law for the normal stress that we learned in the last lectures to determine the elastic displacement of a member subjected to the axial loads. Before we do that, please note that we will neglect the localized deformation caused by the above Saint-Venant's principle, which is usually very small compared to the deformation of the entire members. Now let me explain the example problem. Assume we plan to use a steel column to support a vertical load P. Let's say we know the original dimension of the column and specific weight of the steel. We also know that when we erect the column and use it to support the load, it will deform like the following. Then we are interested in finding the displacement delta of the top surface of the column. So let us see what is the idea to find such displacement. First, we know that displacement or deformation can be found from strain. Second, we know the strain can be found from the stress and the modulus of elasticity using the Hooke's law. Third, we also know that if we can find the displacement for a differential length of the column, we will be able to apply integral to find the displacement for the entire column. That being said, let us consider a differential length element, dl, of the column as shown on the screen. Then, to find the average normal stress for this element, we can consider the equilibrium of the portion of the column on top of it. For that, let us draw the free body diagram of the top portion. From the free body diagram, we can find the normal force NL based on the equilibrium of forces in vertical direction. Next, let us study the deformation of the differential length element. As we already know, the displacement d delta for the differential element is calculated by multiplying the strain with the length of the element. After doing some algebra, we see d delta can be found from the normal force, the modulus of elasticity, the cross-sectional area, and the length of the element. Now the rest will be simple when we just need to integrate this equation over the entire length to find the displacement of the entire column. Please note the following. First, the small l in the bracket of n, e, and a is to indicate these values in general may be the function of the location of the differential length element. Second, as you can see from its development, this equation can be used to find the displacement for any members subjected to axial loads. Finally, in the case when the value of n, e, a are constant over the entire length of the member, the integral equation will be the following. As you can see, this equation is very simple and should be easy to remember. Now let us see the application of the above equation to find the displacement for a bar of multiple segments, each of which has constant normal force, constant elastic modulus, and a constant cross-sectional area. For example, let's say we have a bar of constant modulus of elasticity and two different cross-section area as shown on the screen. The bar is subjected to axial force at different locations, which causes it to deform. Assuming we are interested in finding the displacement delta, then let us see how we can do that. For convenience in our analysis, let us look at the bar before its deformation. Based on the dimension of the bar and loading configuration, we can see the bar consists of three segments of constant normal force, constant modulus of elasticity, and constant cross-sectional area. Since we already know how to find the displacement for each segment, we can simply use algebraic addition to find the displacement of the entire bar. An important note when doing so is a consistent sign should be used for both internal normal force and the displacement. For that, as we can see on the screen, the convention is we will consider both the force and the displacement to be positive if they cause tension and elongation. On the other hand, a negative force and displacement will cause compression and contraction. So that is all the theory for today. In the class, we will discuss this further and have some practice. Thank you and see you in the next lectures.